welcome to Honors Bio, right, for our interesting distance learning. So anyway, we'll just start with something you're familiar with. We're going to start with the scientific method. So scientific method, you've been through it for probably many years, but I just want to make sure we know the steps and what it's for. So the scientific method, so this is use It's used to describe things seen in nature. So things that are naturally occurring, that's what we use the scientific method for. So a lot of times I have students tell me, well, what's the first step of the scientific method? And they say, ask a question. Well, you really can't ask a question unless you make an observation. So I like to say it starts with an observation. So you recognize a problem, right? And you make an observation. So it could be something as simple as looking up on a sunny day, right? Your observation is the sky looks blue, right? So now you need to make an educated guess. So this step right here, one's used to form a hypothesis, right? So a hypothesis, right, is an educated guess, right? But remember, a hypothesis, we're going to say here, must be testable. So if I simply look and say, the sky is blue, right, then I have to be able to test it. It can't just be an observation, but I have to make it testable. So I can say, well, if I go up to different levels of the atmosphere with two people, and I look between the two people, does the sky still appear blue? Right? Well, the sky is made of the same stuff between you and I, right? So if I look between two people, if I looked at you across the table, the sky wouldn't appear blue. It would be clear, it would be translucent. So the sky isn't blue. So really I could reject this hypothesis, right? So now I could change it, right? When they say ask a question. So I could say, why does the sky appear blue? Well, some people say it's reflection of the ocean. I have students tell me that somebody has told them that's reflection of the ocean. Kind of a silly statement. Reflection requires a solid surface and light to bounce between two objects. So in order for it to be blue, there would have to be a mirror sitting way on top of the atmosphere, and the light would have to bounce off the ocean, bounce off the mirror, and bounce back to you. Right? Can't happen. You could say it's refraction of light. Right? So we can see this as light moves through a prism. Right? So blue, right, and then green, and then, oh, should have been an orangish color, and then red further. So we get to all the colors of the rainbow, but green or blue, right, kind of bends the least, right? So since it bends the least, right, in the middle of the day we see that the one that has the longest wavelength is red. That's why at the beginning of the day and the end of the day, the sky's a little more reddish. So it's the refraction of light. So I can perform experiments, and that's what I did here. I used a prism. I performed experiments. And then the important thing we're going to talk about here is I formed the simplest general rule. So when I accept my hypothesis here, I form a theory. And the theory is accepted as scientific fact. So in the English language, when someone says, I have a theory, right? Who stole my pencil? That really isn't correct, because that's not a theory yet. Right? So that's not a theory yet. Right? So a theory has to be well tested. So after you catch the person with your pencil, then you have a theory. Right? So a theory is well proven. So we'll move on from that. So just know the steps. So in science, when we develop tests, the testing phase, which is really important to what we do in biotechnology, we have to identify a variable. And a variable is a single condition. Right, a single condition to be tested. Right. So a variable is a single condition to be tested. Right? And I must change a single condition, right, with each step of the process. So if I'm developing a test, if I'm trying to figure out what makes plants grow, right? Well, plants need sunlight, right? They need water. They need food. They need soil, right? They need all that kind of stuff. If I was going to test if plants grow, I'd have to pick one of these things. Right? Let's say we're going to pick sunlight. So I would have to give every other plant, right, all the same amount of water, the same amount of plant food, the same amount of soil. So these would be controlled variables. Right? And this right here would be the testing or manipulated variable. So that becomes, my manipulated variable. So that's the variable I'm going to change. I could put plants in direct sunlight. I could put plants in the middle of a room where they get a little sunlight. I could put plants in a dark closet where they get no sunlight. And that would be my manipulated variable. But all the plants would get the same amount of water, same amount of food, same amount of soil. When I'm seeing if plants grow, I'm going to check their height. So that's going to be my responding variable. I change the amount of sunlight they get, then I'm going to measure how tall they get. Right? So here's the thing. So these variables go on the y-axis. We often use graphs to indicate information. So when we're graphing, you'll do a lot of graphing. We'll put that. I keep losing my pen. Sorry, guys. So the height on my y-axis. So that's the dependent variable. So my height is dependent on the sunlight. So that's another way to look at it. So this would be your dependent variable. Right? When they often say the x-axis is your independent variable. So you have to pick something. So I'm going to do this over a matter of days. So I could pick something like time. So time is not a controlled variable, it's an independent variable. It's independent of whatever I do. Right? So if I test sunlight, I can go and test something else. I can test the amount of water. But if I test the amount of water, if I make that my manipulated variable, then I have to give all my plants the same amount of sunlight. And then go back and test food, for fertilizer, and I can test soil. So anyway, setting up the control. Right, so control is a situation where no variable has been changed. So that's what we talked about above. Right? If the testing supports your hypothesis, we pick another variable and we retest. We just talked about that before, so I'll just move on. All right, so here's a subject that makes people confused. So I'll just introduce it and then I'll reinforce it through the semester. I just want to teach you significant digits, right? Right, so significant digits are all digits Right, so all digits in a measurement and one estimated digit. This one estimated digit increases. Increases accuracy. Right, so that one digit increases accuracy. So if I look at this measurement on this triple beam balance, here I have 0. Here I have 20 grams, and here I have 6.4 grams, right? So I have a 0 here, I have 20, I have 6.4. So I have 26.4 grams. So those are the real measures. So those are the real measurements. But if you look at that line right here, you'll see that it's not on 6.4. It's kind of halfway between 6.4 and 6.5. So 0.05 grams is estimated. Right? Because what you're saying is it's not 26.4, it's more, but it's not 26.5. So I would have to say this is 26.45 grams. So we always do that in science. We always estimate the last digit. You know, if you ask my son how old he is, he'll say that he's almost 15, right? He's not 15 yet, right? He's not 14. In fact, his birthday's in like 2 weeks or 3 weeks, right? Almost 15 is his estimation of where he is, right? So it just increases accuracy. All right, so we'll move on. So same thing here. Right here I have 10. Right here I have 20. Right, so halfway between 10 and 20 is 5. Right? So 15 milliliters is my real measurement. Right, and then I can estimate halfway between 15 and 20. Maybe 2.5 is my estimation. So I can say it's 17.5, right? Would probably be my estimation. Okay. All right. Rules having to do with zeros. So numbers. Numbers are a reference to measure. So all numbers are reference to a measurement. So there's two things involved here. There's precision. There's precision and accuracy. So if I'm playing darts and I want to hit the bullseye, and I throw 3 darts, I hit one here, one there, and I throw a second set of darts. I hit one here, one there, and one there. So the red one is precise. So it has great precision because every time I throw the darts, they land in roughly the same place. So I have great precision. I'm not a very good dart player, but I have great precision. And this shows accuracy. So accuracy is close to your intended result. So I wanted to hit a bullseye. I hit one bullseye. I hit the target some other place, and I missed one completely. But I got my intended result. So there's a difference between precision and accuracy. Precision is decimals. Right? Precision is decimals. Oh, I didn't write that very well because I was running out of space. So we can say that precision is your decimal place. So 0.001 and 1, so this has greater precision. Right? Because it's to the 1,000ths, and this is just to 1. Right? So this has greater precision. Accuracy is close to my intended result. So precision and accuracy, two different things. But I will show you what we mean. So when I measure, right, I have rules, right? Trailing zeros, here's the rules we got to follow. Trailing zeros without a decimal are never significant. So this one has 2 significant digits. The 3 zeros at the end just tell me that the magnitude or the size of the number, right? 13,000. So this has 2 significant digits, right? If I said 13, oops. If I said 13,000 with a decimal point, right? I would have 5 digits because a decimal point would tell me where my precision was in that number. This number 13,000 over here is not very precise. Zeros that are leading are not significant. So again, this has 2 significant digits, the 2 and the 7. The zeros before it just tell me where I start to count at. Right? Very precise number, not very many significant digits. So here's number 3. Trailing zeros after a decimal are always significant. So if you look at this number, this has 5 digits. The decimal point up here tells me where I start counting from. I start counting from the 100th place, and I count over. This is a very precise number. This number here has 3 digits. These 2 zeros at the end are not significant because there is not a decimal point. Right? So remember, the decimal point will tell you where the precision of the number is. And the zeros found between are significant. Right? So all the numbers are significant because they're between 2 real numbers. Right, so really quickly because we're running in time here. When I multiply, right, so your answer could only have the number of digits with the operand with the least number of significant digits. So this has 4 significant digits, this has 3, so my number has to be rounded to 3 digits. Okay? Addition, subtraction. So addition and subtraction, right? So answer can't be more precise than least precise measure. So this one is precise to the tenths, this one is precise to the hundredths, and this one is precise to the tenths. So your answer has to be in the tenths, right? So even though you type in your calculator and you'll get this number here, right, you have to round it to the tenths place, right, because that's the least precise measure. So we'll work on that. And I'm not going to grade you significantly on that, but I want to introduce you because I'll continue to have that conversation. It'll really help you out in chemistry if you understand it now. Scientific notation, we need to be able to do that. So scientific notation is how scientists take really big numbers, right, that are unmanageable, and put them into numbers that are small enough and follow the rules of significant digits. So the important thing to remember, scientific notation, right, is a real number followed by a decimal. So all I'm going to do is followed by. So if I said 20 plus 20, right? So remember, I'm doing addition. So that trailing zero doesn't count, and it has to be accurate to the tens place. If I'm going to put this, so this is equal to 40. If I'm going to put in significant or in scientific notation, 4 times 10 to the 1, right? Because I took a 10 out of here, right? But it'd be 4.10 to the 1 is more correct. I couldn't do 4.0 times 10 to the 1. That would be wrong because this one has 2 digits. This one only has 1 digit. So that's the way that works. Okay? You couldn't put 40. Right? So scientific notation. If I make things bigger, right? If I make things bigger, I make my exponents smaller, and if I make things smaller, I make my exponents bigger. Right? So this number here, right, Avogadro's number, right, I have to count 23 places I move my decimal, and that's why this says 23 here. So I made this big number smaller, so I made my exponent here bigger. Right? If I take this number, which is a very small number, and I move my decimal place, 1, 2, 3, right? So I made this small number bigger, so this becomes smaller, more negative. Okay? So that's all there is to it. Good luck today in your math. There will be a math key for you to look at, and thanks for watching.